Yeah.
And so when they go past the fixed contacts, they make contact.
So they get it off the core contacts.
Yeah, because there's juice feeding in this way.
Yeah.
And so that the electricity goes in and powers the magnets inside.
Yeah.
Which fires the drive mechanism, which I'll show you right now. So you grab the ball, and I split it in half. So you can see inside the two halves, yeah? At the top you've got 3 active magnets and 2 passive magnets. They're just normal, natural magnets. And these are electromagnets that are fired by that switching mechanism that I just showed you that arrangement of. And the reason why there's 2 and 3 is so that whenever the top magnet and the bottom magnet are lined up, the next magnet is already attracting it.
Oh, to move it.
So it counteracts the pullback, because even though that magnet switches off and becomes mostly non-magnetic, the next one switches on and attracts towards the next one.
Yeah.
But you don't have 2 lining up both at the same time, because then you get an I'm stuck situation.
Yeah.
Only one lines up at a time and it goes around 1, 2, 3, 1, 2, 3.
Yeah, I understand that.
I've made a basic diagram of how the switching mechanism works, the switching sequence. The fixed contacts are this inner circle here. That very inside circle is the axle. This is like a top view chopped. That would be like your axle, and these numbers around here are the contact points on that fixed switch arrangement with electricity. And then you've got the top half and the bottom half drive magnets. 3 on the top that are active magnets and 2 on the bottom that are passive magnets. Here in this picture you can see that the green one is lined up with the red one over here. It's like starting position. And I've put arrows there so you can see that red ones go this way and the green ones go this way, because it's like a differential gear arrangement. And they're facing each other so that they have an attraction. It's basically 12 switching sequences for one full revolution.
Yeah.
What I've done here is I've got a simple animation that I'll show you. This is just a still snapshot, but you get the idea. If you look at the first couple, you've got the active 1 and the passive 1 lined up. You can see that the number 1 switch, because what I've done is each of the active magnets has got a color: blue, a red, and a green.
Yeah.
And each of these switches have got 3 colors: red, green, and blue. The idea is that when the blue line for the blue magnet is lined up with the blue contact, the contact goes through and switches on this electromagnet.
Right.
These ones aren't lined up. That's red and green, and that's green and red. So they're not switched on. They are like not magnetic. So in this picture, that one would be on. And these 2 are in close proximity, and they attract one another. And then as they attract one another, this goes past that fixed switch and turns off. But then the next one is on, attracting, and then the next one is on, and the next one is on.
Yeah, got that.
Yep, and that's how it works. You can see that in motion. That pulls towards that one, it's on. When these 2 meet in the center, because one is going one way and the other is going the other way, the next one is turned on. Or just prior to them meeting, turns on. And this one is now attracting that one. And around it goes. I have a simple animation here that I'll show you.
Yeah. Is this real speed animation, is it?
No, because the device runs very fast.
Very fast, is it?
Very fast, yes. It's good to use very strong magnets. It's not supposed to be as pausey and stuff, it's just a bit of a dodgy animation. But you get the idea. They switch as they're approaching each other. If we follow this one, as it's approaching the next partner, it switches on and switches off, switches on and off. So it drives and drives. When it's got the yellow ring, it's on, pulling it around. And one is always on.
Oh, right.
You see. And you notice as it turns on, it's approaching the next one.
So that means, in theory, you can theorise that it's only ever moving due to the actual juice coming from the yellow magnet, and the other ones are just having to behave in that way, but are effectively dead.
Yes, correct. And
but
you
they
don't
have to follow that
need
pattern because of the spacing and the chamber.
Correct. And the thing is that when an electromagnet is activated, it has an incredibly strong pull.
Yeah.
Even with a reasonably small amount of juice, you can make an electromagnet have an incredibly strong pull. And when it's attracting towards another magnet, even if it's a natural magnet, then it's an even more incredibly strong pull. That pull is very, very strong, which means that it's the torque that this thing has, that all of the forces of turning those 2 fans around to blow through cooling air, and all of the resistance of all of the coils interacting with all of the moving magnets and all of the forces causes a lot of resistance.
Yeah.
Right, it's very resistance that pushes electrons down wire to make electricity, but it causes resistance and makes it harder for the machine to pull around. You follow my meaning?
Yeah, I do. Yeah.
And if it were a weak engine, it would be an issue. But this, no problem, because it's got an incredibly large amount of torque. That's what I'm saying is very underrated about the basic power of a simple electromagnet. How strong is that? And how much juice are you putting into it? Do you know what I mean? Very little. And this is why I've called it the differential generator. Because essentially that's how it works. It's two halves, one going one way, the other going the other way. And it's a clever trick. And it happens very quickly. Very efficient, a clever, simple little idea.
Oh, I see how it works.
And this is also why I've spent a lot of time on this idea, is because I believe it's a fresh idea. It's a new idea, completely. No work that I've ever come across.
Seems crazy that they wouldn't, doesn't it, as well, when you sit and have it explained to you, it really does.
Yeah, that's right, because it's very simple. It's just magnetic attraction driving around magnets inside coils. This arrangement fits inside this arrangement, and it's held in place with the two bearings at the top and these gears. That's it. And then it's all holding together because it can't go anywhere upwards because it stops where the bearings go. It goes through the bearings to drive the fan and stuff above.
Yeah, I understand that.
Yeah, because if we step back a bit and I show you the whole machine there, you can see you've got all of the magnets in the actual half of the core balls which spin around, because in the bottom halves inside here is where that switching arrangement takes place. So it's like the top half and the bottom half attracting and driving each other around, one way and the other way. I've tried to make it as efficient as possible, and I'm hoping that someone who sees these designs, it will make sense to them why I've done it that way. I've tried to do the very simple things.
Yeah.
I've built in a bunch of temperature probes on all of the various coils and bearings,
right,
so that you can keep. This is a prototype, so you don't know. An RPM meter on the other control box. This is the main VA control box. It just measures what volts and amps are coming out of each of those 6 top coils. The big fat main coil at the bottom, and each of the 6 middle small coils in the middle. And my idea for controlling the mechanism is a very, very simple one, and it works like this. The more electricity you feed to an electromagnet, the stronger the magnet.
Yeah.
Right?
Yeah.
The more the magnetic attraction.
So the more you feed it, the faster it's going to be.
Exactly.
Yeah. Okay.
And so the faster it'll go, and the more powerful it'll be. So you basically have a simple control knob, volt adjust, and it adjusts the amount of voltage feeding to those 3 active magnets switching in turn. And the higher the voltage, the more they attract, the faster the thing spins. You lower the voltage, slow down.